Okay, this video is picking up where the last one left off. We had just finished talking about composite members in which the load is shared by the two members, such as the example problem we're about to look at, which is example 1111. So, example 1111. And in this problem, we have a steel pipe. It's a hollow pipe, cylinder shaped, and it's filled with concrete. We apply a compressive load to it equal to 100,000 pounds, which of course is equal to 100 kips. The pipe is a 6-inch diameter standard weight pipe, and the concrete is 3,000 psi concrete. The pipe is made of ASTM A501 steel, which means that all varieties of steel, have a modulus of elasticity of 30,000 KSI. So we're going to assume that we apply this load of 100,000 pounds to it, and that it's going to deform equally. So there's going to be some deformation from its original length. It's going to shorten. Both the steel and the concrete are going to shorten the same amount. What I want to do is find the stress in the steel and find the stress in the concrete. Okay, so first of all, let's look here at what we have. We've got a 6-inch diameter standard weight pipe. So what we need to do is look up in the appendix. I'm looking at Appendix B, selected pipes. It has both standard weight and extra strong. So I'm looking at standard weight. 6-inch pipe has an area of 5.2. So our pipe area is 5.2 inches squared. And the inside diameter is equal to 6.07 inches. So pipe is nominally designated by its inside diameter. Our pipe is a 6-inch diameter, but you can see it's not exactly 6 inches. It's 6.07, which is why it's important to look these values up in our appendix. And so what that means then is that the diameter of the concrete that's filling in our pipe has a diameter of 6.07 inches. So the area of the concrete is going to be equal to pi d squared over 4. So that's pi times a diameter of 6.07 squared divided by 4. And that is equal to 28.94 inches squared. So I have my area of steel of 5.2 square inches, and I have my area of concrete of 28.94. Now, the problem statement told us that our concrete had a compressive strength of 3,000 psi. The only reason why that information is relevant is because if you look in the appendix, and is Appendix G. So from Appendix G, we have the material properties of several different materials, including, if you look at the bottom of the list, there are 2 rows for concrete. One is 3,000 psi concrete, and the other is 4,000 psi concrete. You can tell that by looking at the ultimate strength column, and one is given as 3 ksi and the other as 4 ksi. So we want the 3 ksi concrete, and with concrete, the modulus of elasticity is a function of its compressive strength. And 3,000 psi concrete has a modulus of elasticity of 3,120 ksi. Looks like, let's see, yes, modulus of elasticity in ksi, 3,120. And steel, regardless of what type of steel it is, has 30,000 ksi. Okay, so let's scroll down here a bit to give us a little bit more room. So that means our modular ratio is equal to the modulus of elasticity of material A over the modulus of elasticity of material B. So here's where it doesn't matter which material we consider to be material A and which B. We can call steel A or steel B so long as we are consistent throughout the process. So I will call steel material A, but you could do it the other way around and still arrive at the correct answer so long as you are consistent throughout your process. So the modulus of elasticity of steel is 30,000 ksi, and the modulus of elasticity of concrete, we just looked that up, 3,120 ksi. And so the modular ratio is equal to 9.615. I'll carry out an extra significant figure for now. So 9.165. That is our modular ratio. And so if I scroll over here and down, here's the formula that we had come up with at the end of the last video for finding the load and or stress in a composite material that's laminated in the way that this is. So let me come back over here. So we are saying that the total load is equal to the stress in material B, which we are calling the concrete, is equal to, no, I'm sorry, not equal to, but multiplied by the modular ratio. Let me undo that. Yeah, I can do. Let's fix those little mistakes. Here we go. Multiplied by the modular ratio times the area of material A. Now I called steel my material A, plus the area of the concrete. So that's a common mistake I've seen made, is getting these two materials mixed up. I scroll up here. We arbitrarily chose to call steel our material A, and so we have to stay consistent with that. This has to be material A, and this material B, in order for this formula to work. So the total load applied to this material was, let's scroll back up and see, 100 kips. So I have 100 kips load is equal to the stress in the concrete, which I don't know, multiplied by the modular ratio, 9.615. Let's fix that 5. Bracket here. 9.615 times the area of the steel, which was 5.2 square inches, plus the area of the concrete, which was 28.94. So I can now solve this formula for the stress in the concrete. The stress in the concrete is going to equal 100 kips divided by 9.615 times 5.2 plus 28.94. And when we work that out, we get an answer of 1.267 KSI. So that is the stress in the concrete. Now if I want to find the stress in the steel, I need to find that formula. Where did it go? Right here. The stress in material A is equal to the modular ratio times the stress in material B. So we had found that out earlier when we derived our formula. So let me scroll down and over. And so the stress in material A, which is the steel, is equal to the modular ratio times the stress in material B, which is the concrete. So that means it's equal to 9.615, which is our modular ratio, times 1.267 KSI, which is the stress in the concrete. So if I multiply those together, I'm getting 12.18 KSI. So it's interesting that there is so much more stress in the steel versus the concrete, but that's because the steel has a much higher modulus of elasticity. And so because it is so much stiffer, it carries more of the load. So that answers this question. That's the end of this example. We have found the stress in the concrete and in the steel for a laminated composite material. One more video to go, and we should be wrapping up Chapter 11.